than 40 people now connected. So it's a real pleasure to welcome today Professor Avishai Dekel. So Avishai is a professor at the Hebrew University of Jerusalem. He's an expert in galaxy evolution and cosmology. He has made during his career real key contributions to the field of cosmology and galaxy evolution, studying, for example, the effects of supernova feedback, also how gas is fed into halos. And probably most of you know many of his works. So today, so he was invited to give a colloquium at the IAC. So it's a pity he could not come physically, but this is what we have now. So instead, he will give this colloquium online, and I hope we will all appreciate. So today he's going to talk about the golden mass of why there's a golden mass for galaxy evolution, and his take on this. And so.
Okay, thank you, Mark. I really regret not being able to visit you, and I hope your invitation will be extended for next year or whenever we'll be able to travel. And it's a great honor to give you a lecture, share with you some of what I think is interesting in galaxy formation. And I'm going to tell you about the golden mass of galaxies and black holes. Please be free to ask questions during the talk and be interactive, so I know that I'm not talking to my computer alone. So this is one reflection of the golden mass for galaxy formation. What you see here as a function of halo mass is what I call the efficiency of galaxy formation. It's the stellar mass to halo mass ratio. And you see that at all redshifts, actually, there's a peak. And the peak is at about 10 to the 12 solar masses in the halo. That's the golden mass I'm talking about. Most efficient galaxy formation, star formation in halos in this mass, around this mass, much less efficient on smaller and higher mass scales. This is what we call the low mass quenching, and this is what we call the high mass quenching of star formation in those halos. It turns out that the black holes also know about this golden mass, and they turn out to show up as AGN above this critical mass, much less below this critical mass, so they know about it. In fact, the same mass scale can be read from this picture. This is the history in terms of redshift of the star formation density in the universe, the so-called Madau plot. And as you see, there's a peak around redshift 2. Now, I argue that this peak is not only a peak in time, it reflects the same golden mass. And this is because, and I'm saying that the early times is the low mass quenching, because all the halos were low mass. And here, where the high mass halos trying to form galaxies, it's the same high mass quenching. And the reason is that if you follow the typical halos that form at any redshift, what we sometimes call the pressure mass, nonlinear mass, this mass at redshift 2 is comparable to the golden mass. So the typical halos that form at redshift 2 are halos in the golden mass for peak efficiency of galaxy formation, and that's why you see a peak at redshift 2. It's not a special time, it's a special mass that comes and expresses itself at the same time. Recently, people noticed that the same scale is imprinted on the black hole evolution. This is one example. the fraction of galaxies with AGN, a paper by the Munich Genzel group, many galaxies. Well, what you see here, doesn't matter which line you want to follow, as a function of stellar mass. Below stellar mass of 10 to the 10.5 solar masses, there are not many strong AGNs. Namely, the black holes are not very big and not accreting very quickly. Above this golden mass, this is a stellar mass in this case, which corresponds to about 10 to 12 solar mass in the halo, you have a steep increase in AGN frequency, namely in the accretion onto the black hole. And the same scale is imprinted here in the black hole evolution. So the question I want to try to answer today, at least partly, is why do galaxies tend to form near this golden mass? And second, why do black holes care about it? Because we don't have a very specific reason in the physics of black holes that points to this golden mass. And I try to argue that it comes from the golden mass of galaxy evolution that imprints itself on the black hole evolution. So let me just start with a summary. If you just want to go home after this slide, you can, because everything is in this slide. This is the golden mass, a typical 10 to the 12 solar mass in the halo, 10.5 in the stars, and potential well with a real velocity or rotational velocity of 10 kilometers per second on the order. I'm going to blame supernova feedback, which is effective below this golden mass, to be responsible for a lot of this appearance of golden mass. On the other hand, from the high mass end, I'm going to blame the gravitational heating of the halo, or the CGM of the halo, circumgalactic medium, by Virial shock heating. And then I'm going to tell you about a phenomena which has been discussed recently, the compaction to blue nuggets, which causes quenching. I'm going to argue that this is a critical sequence of events for the golden mass of galaxies and of black holes. And then I'm going to tell you that black hole growth is suppressed by this supernova feedback in galaxies below the threshold mass. And then there's the compaction event drives the black hole growth at higher masses. And I'm going to end up with talking about general quenching of massive galaxies, why they don't form stars very efficiently. And I'm going to end with a very recent work about ring formation in the early universe. So let me start with supernova feedback in low mass halos. Supernova, the idea is that supernova-driven winds push the gas out and suppress star formation in low mass galaxies. This is a nice movie that Ariana may know from the Nihau simulations. You see supernovae explosion in a dwarf galaxy and just get the impression of how effective it is for the whole galaxy, actually. Every supernova event is so dramatic, and it really governs the evolution of the galaxy by heating and removing the gas from the galaxy. If you look at the scales as a function of redshift and virial mass, this is the typical halo, the pressure sector mass. This is where the typical halos that form at any given time. Today, it's a group of galaxies, but in the past, it rises very steeply. And this is the critical mass below which supernova feedback is effective. And above it, it cannot affect the galaxy. And this is a velocity of 100 kilometers per second. It's not exactly a fixed mass. And that's the basic result of Dekel and Silk from 86. And the way it's derived is very simplistic. we just compute the energy fed to the ISM by supernovae. It is proportional to the mass in stars eventually, and a characteristic velocity of supernova, which is about 100 kilometers per second. And you want to compare it to the binding energy of the gas in the galaxy, in the halo, which is m gas times the velocity squared. When you compare them, you end up with this upper limit for effective supernova feedback, and that's this line. Very simple argument, but very, very powerful. The second scale is the Virial shock heating. I'm talking about results from more recent analysis by ourselves, but it's really based on ideas by people years ago. And the idea is that, this is a simulation, the idea is that at the Virial radius, if you are above a critical halo mass of 10 to almost 12 solar masses, you end up with a stable shock at the Virial radius. So the gas that comes in from the outside is heated to the Virial temperature. And the condition for supporting a stable shock is that the cooling rate is slower than the dynamic and compression time. Then you can have a stable shock, and then you get a whole CGM, and it turns out you can, because the cooling time is a function of the halo mass or halo velocity, you end up with a critical mass for this. So this is the other scale. And if I plot this scale here, this was discussed in this paper, it's a pretty much constant mass, just below 10 to the 12 solar mass for the halo, above which you had a hot circumgalactic medium at 10 to the 6, 10 to 7 degrees, depending on the halo mass, below which the gas falls in cold, does not heat up as it crosses the Virial radius. There's fine tuning to this, that you can have cold streams penetrating the hot CGM if you are below this line. This was crudely predicted in this paper and then kind of confirmed in simulations. And this is what gives you high star formation rate above redshift 2 in star forming galaxies that already have a hot CGM, but they have the cold stream penetrating in. These are the cold streams I'm talking about that penetrate the Virial shock and go all the way and build the galaxy in there. That's the main mode of galaxy formation at high redshifts. Now, observationally, this is confirmed by people who look at galaxies, count them, and abundance match them to dark halos from lambda CDM simulations. And in this figure, in the same diagram, you see the fraction of star-forming galaxies. A lot of star-forming galaxies here, a lot of quench galaxies here. And this is the prediction from the previous slide, the theoretical prediction. Indeed, you see that the universe behaves roughly like what this very simplistic theoretical prediction tell you, that you have quench galaxies above this mass and star formation below this critical mass. So if I put everything together, the supernova feedback, the Virial shock heating, and the pressure ejecta mass for typical halos, you see that they all converge to a critical mass at low redshift, between redshift, I would say, 2 and 0, which is just below 10 or 12 solar mass with some big uncertainty. And that's the origin of the golden mass, of why you have maximum efficiency here and minimum efficiency here because of supernova feedback, and here because of CGM heating by gravitational energy that falls in. Now I'm going to tell you about this event of compaction, which really make a big impact here on the implications of the golden mass between those supernova zone and CGN zone. So it all starts with people observing red nuggets. These are galaxies redshift 2, typical masses of big galaxies, but compact, small effective radius. These are passive galaxies with low SFR. That's why they were called red nuggets. And the question is, how do you get at the early universe such compact stellar systems? Well, you must have some dissipative process. You have to lose angular momentum and energy, and the only thing that can do it is gas. Stars cannot do it, cannot compactify. Gas naturally compactifies if you allow it to lose angular momentum drastically. And that's the idea of red compaction. Just by observing the red nuggets, which are very frequent at redshift 2 or 3, you can guess that they're going to be what I call blue nuggets, namely very compact gaseous systems that form stars and make the red nuggets. And this is indeed the blue nuggets, which were discovered a little after the red nuggets. The funny thing is that they're also red, but they're red for the wrong reason. They're red because of dust. They're star-forming, compact, 1 kpc gaseous systems. And I think now we all believe they are the progenitors of the red nuggets. Of course, they live much shorter, so it's harder to find them. Once you become a red nugget, you remain red and compact, at least at the center, but the blue nugget just come in for a short while before they passively kill the burst of star formation. So now I appeal to cosmological simulations, mostly the Vela simulations that we ran in our own group. The nice thing about it, it's the highest resolution simulation, cosmological. 25 parsec is the resolution for the gas. And we have a suite of 35 galaxies that we studied. Many people are collaborating. I highlighted someone you know who became part of us working on these creatures. So here's a little movie from simulation at very high redshift, 36. You see cold streams feeding this galaxy, which becomes very clumpy. And the collisions between those streams make angular momentum loss, and the gas falls into the center and create a blue nugget in the center here. This is a very high redshift, these galaxies. You might have noticed on the archive recently, people reported an ALMA discovery of a very redshift 4, this galaxy. This is a redshift 6 to 4, this galaxy in the simulations. And at the very end, I'll tell you about why I think these are formed also very high redshift in massive galaxies. So this is the compaction process. This is the gas. This is the stars in 4 steps. You see the gas is contracting to the very center, 1 kpc, that's the blue nuggets. And it forms stars right there. You get this very compact bulge, which become a red nugget. And more stuff is coming from the outside by mergers and so on. You see that the gas eventually form a disk and a ring. And this is coming from newcomers, the new streams. It's not that the gas from here is pushed outside. It's new gas is building this, and I'll talk more about this at the end of my talk. This is the compaction, this is the blue nugget. This is the central depletion of gas ending up with a nice star-forming gas ring. And this is the red nugget that we talk about. So schematically, if you look as a function of time and mass, what the gas is doing, it compactifies by a factor of 10 maybe in mass inside the inner 1 kpc. And then the star formation here and supernova feedback causes this depletion. You can refer to this as the star formation rate, also following the Kenneckett relation between star formation and gas density. So this is the star formation rate schematically. We see it in one version of another in the history of almost every galaxy in the simulation. This is what the stars do. Once you have a compact blue nugget, you end up with a compact red nugget because stars are formed in this burst of compact gas. Observationally, this is a prediction from the simulations. If I plot here some measure of compactness, which is the stellar density inside 1 kpc, and I plot here the star formation rate, the specific star formation rate, you see an evolution from diffuse state to a compact state as a blue nugget. This is the compaction. And then the trigger of quenching into a red nugget. And you have this very nice L-shaped evolution. These are 8 galaxies from the simulations. Observationally, this is what you see when you look at many Kendall's galaxies and you stack them together. This is in a paper by Barrow et al. And you see the same L shape, except that now you can tell the evolution track. By just looking at the picture, you could not tell where things came from, just the L shape. But now you can tell from the simulations that this was the evolution track. Okay, you may ask, what is causing this wet compaction? Well, many things can do it. The main one is mergers, because merger is a great way to lose angular momentum for the gas and let it sink to the middle. But there are other processes. I just listed several of them. Let me show you 2 examples. Well, one is the mergers, of course. So this is the great way to lose angular momentum and have the gas go to the middle and create a blue nugget. This is a large-scale simulation of gas in the cosmic web. You see the galaxies the galaxies are formed at the nodes of the cosmic web. And you see that they stream along the streams and merge. In this case, all end up in one merged galaxy here. So these are the mergers that allow you to get several compaction events. These are manifestation of counter-rotating streams that collide and lose angular momentum. As you can see in those 3 cases, that 2 streams have the same orientation of angular momentum, but one stream has an opposite orientation. Typically, it's 1 against 2. So these guys, they determine the angular momentum of the disk here. This one just collide with these ones, end up with 0 angular momentum here, and shrinkage to the middle to create a blue nugget. And there are several other mechanisms which I won't go into. Okay, now a key point is that first, how do we connect the theory to observation? And that's where Mark comes in. We developed some ideas of how to use machine learning to compare theory predictions to observations. And this was one example when we wanted to see the existence of blue nugget and their properties. So we take galaxies from our simulations, identify blue nuggets, and then identify galaxies in the pre-blue nugget phase. They're usually mergers or some irregular gas morphology. And then post-blue nuggets are typically nice disks or rings with a red nugget in the middle. So we classify them into those three categories. Then we observe them as if we are HST. We make mock images of the same galaxies by putting in dust and by putting in all the limitations, resolution, PSF, etc., no background noise of the HST in the candle survey. And this is what they look like: pre-blue nugget, at the blue nugget, and post-blue nugget. And we train a CNN, a convoluted neural network machine, to tell by looking at those pictures in different wavelengths, the different HST colors, and try to classify them according to what we know they should be. And then we go to observations. And these are three cases which the machine classify as blue nugget, pre-blue nugget, and post-blue nugget. It turns out to work very well. We find many blue nuggets. And as a function of stellar mass, this is a number, fraction of galaxies we identify as pre-blue nuggets. They dominate at low mass, post-blue nuggets, and most important, the peak of the blue nuggets. So it turns out that the blue nuggets, as defined by the simulations, not only exist in the real universe at high redshifts, but they also exist and prefer the same golden mass that the simulations tell us about 10 to the 10 solar mass in stellar mass, the same golden mass. So these compaction events really happen at the same masses, and we think it's because of the same reason that the golden mass exists in the first place. It's because supernova feedback suppresses compaction events that try to compactify at low redshift. And the fact that the CGM is hot, maybe also AGN feedback, suppress the compaction above the critical mass, allowing major compactions where the density really grows by a factor of 10 to occur mostly at the golden mass, or near the golden mass. Now, this compaction event, the blue nuggets, BN is for blue nuggets, they cause many transitions in galaxy properties. And I will mention one or two. I will not spend much time to tell you about the glory details. They take diffuse galaxies and make them into compact core galaxies with extended ring and disk. They cause the trigger of quenching of star formation. I'll tell you about how they produce a narrow main sequence of star-forming galaxies. Dark matter dominant centers become baryon-dominated, and systems which are typically prolate and dominated by dispersion velocity become oblate and dominated by rotation, and many other things which I won't talk about today. So here's one example. This is the picture you showed before. And now I plotted dark matter at early time before the compaction event. The center, 1 kpc, was dark matter dominated, but now it becomes stellar dominated or baryon dominated. This is a very typical feature that defines the major compaction event. This is shown here as a function of stellar mass. You see the baryon of a dark matter at the center is going up and up, and you end up with baryonic dominated galaxy in massive galaxies. Actually, there are recent observations that indicate low dark matter function in massive galaxies by Genzel and company. Without telling you the details, we have an idea for why this transition makes the shape change from prolate, which is above this line, to oblate. I'm not telling you what is the measure of shape that I'm using, but this is the basic result. Prolate stellar systems become oblate because the dark matter dominance goes away and you get baryon dominance. And again, I won't go into great details, try to explain this, but those two things are very related. If somebody would have some question, I'll be happy to answer. One thing I do want to mention about the transition before I go on to the black hole is the fact that we have a star-forming main sequence. If you plot stellar mass and star formation rate, the star-forming galaxies really like to be in a blue cloud, star-forming main sequence. And the question, why is it so narrow? This is the picture. And what I'm plotting here is again specific star formation rate normalized to its redshift evolution. And the connection to the blue nuggets is that we think that compaction events take the galaxies to the top part of the main sequence, and then the quenching take them down to the red sequence to become quenched through the main sequence. And we can make predictions based on gradients of galaxy properties along here, from blue nuggets to red nuggets. And indeed, these are observational results in the line here. This is the gas fraction as a function of deviation from the main sequence up and down. So above 0 is above the main sequence. You see a slope here, and you see also a slope in a depletion time of the galaxy, which is the gas mass over the star formation rate. This is the observation. And at this point, each point is a galaxy in a simulation. You see that this transition recovers the same slope that we see observationally. And the key is that this transition occurs at the golden mass. This transition, if they happen several times, explain why the main sequence is narrow. And I won't go into details here. Before I move on to black holes, does anybody has a question about compaction or anything else I said that I can help people follow better?
Okay, I have a question, if you allow me to do. So this is Jorge Sanchez Almeida. It's about the evolution of the metallicity during this compaction and quenching. So I presume that they are strongly related with the evolution of metallicity. So during the blue nugget phase, the metallicity has to be very low because you have plenty of gas. Whereas when you have the quenching phase and you get rid of the gas, then the metallicity have to increase. And could you say something about that and whether that thing you think is connected with the fundamental metallicity relation?
Yes, we do recover the fundamental relation where the metallicity goes up with mass intensity off. I may make a comment about this when I talk about rings at the end, if you allow me.
Sure.
And maybe I'll go back to your question at the very end, okay?
Sure.
Okay, let me move on to the black hole. And again, I told you that I think that the black hole growth is very much influenced by the galaxy evolution, in particular the compaction. So this is a nice simulation by Johan Dubois and al. As a function of time, there are two different simulations, one with supernova feedback and one without supernova feedback. And this is the black hole mass. what you see here is that the evolution without supernova feedback, which is this, the black hole started growing at the very beginning of the simulation. Very rapid growth all the way. Nothing stopped the black hole from growing. But if you put in supernovae, you suppress the black hole growth for a while. And then there's a magic time, and the black hole starts growing. You won't be surprised if I tell you that this happens when the galaxy is at the magic golden mass. What really happens is a merger. You see this galaxy coming in, merging with this one, and you see the effective radius suddenly goes down drastically because you made a compact blue nugget right there. But the main lesson is that supernova feedback is responsible for suppressing black hole growth simply by removing the gas from the central region. The same gas, which is the gas supply for the black hole growth, is gone. But remember, at the magic mass, supernova feedback is no longer effective. So the black hole can grow freely. And that's the idea. We study new simulations called the New Horizon simulation, also by Dubois et al. And we see things like this. You see as a function of expansion factor, which is time, if you want, and mass, you see the gas mass within the inner 1 kpc compactifying to a blue nugget. And a little after, you see the black hole growing, actually starting right where the compaction started, the black hole growth also started. This is the black hole mass multiplied by some factor to put it in the same picture. So it looks like the compaction really triggers the black hole growth. We see this in many simulations. We ask ourselves, how exactly does it work? It turns out that because of the compaction, the potential well, which is marked here by the velocity, circular velocity squared, is becoming deeper. And this deep potential well pushes everything inwards, including the black hole orbit. It's like a diabatic contraction of the black hole orbit because of the deepening of the potential well caused by the compaction event. And this is the radius of the black hole. You see the black hole used to wander around the center of the galaxy at 1 kiloparsec or so. Nothing kept it locked to the center. But once the compaction occurred, the potential well became deeper. The black hole orbit is pushed inwards by adiabatic contraction, and they also drag dynamical friction on the dark matter and gas that now fills the center. And the black hole shrinks to a radius about 10 parsec around the center. And from there on, the black hole really looked to the center. Here it was moving quickly, and there was not much gas around it because it was driven away by supernovae. It was not really accreting much. But here at the center, it's in the middle of everything. A lot of gas came in by the compaction event, and the black hole can really grow very quickly. So the black hole now is subject to compaction event, is making this big jump as it enters the green valley where galaxies started to be quenched. These are 7 different simulations or the same galaxies to the same simulation. And you see how the black hole mass is growing as a function of stellar mass with the same L shape. suppressed by supernova feedback, free to grow when it sinks to the center. These squares mark when exactly the blue nugget phase was. And you see it's pretty much in the knee where the change of the evolution track is happening. This is not specific to the New Horizon simulation. Every simulation that has a black hole reproduces the same features. This is so-called Eagle simulation with no supernova, no feature, with supernova, suppression and rapid growth at the critical mass. The fire simulations, similar behavior. So this is a very robust feature in the evolution of black holes and galaxies. The new point that we point out is that the compaction is really happening right there and make this transition very sharp. So this is a summary of what I just said. There's a supernova phase, pre-compaction, below the golden mass, where black hole goes to suppressed. There's a post-compaction event phase, where you have a hot CDM phase above a critical mass. Black hole growth can continue, but the trigger is the compaction event, which is confined to the same golden mass. It really activates the rapid black hole growth. Observational evidence for this, I'll show you two of them. This is something we did from candles. Star formation rate is now upside down, and compactness as before at the effective radius. And the color tell you the fraction of AGN in the different regimes. You clearly see that there's a high peak, high fraction of AGN activity in galaxies once you become a blue nugget, after compactifying and before passively evolving to the red nugget phase. That's exactly what was predicted. I showed you already this result from Foster Schreiber, Genzel et al. And I want to reproduce this from the simulations. For this, I really need to look at the accretion rate in the black hole as a function of stellar mass in the different galaxies. And then I assign a luminosity by a very simple rule from the accretion rate. And I put a threshold, maybe this luminosity, and I say I observe only AGNs above this threshold. Or I can choose any other threshold, depending on the survey. What I find is that the fraction of AGN, depending on the threshold, is one of these L-shaped lines, depending on the threshold I chose. This red line is the observation line. So you see that the blue line is really a nice match. Actually, if I translate their luminosity selection to the simulations, it's the green line. So the critical mass is a little smaller. It may be true or maybe an artifact of the simulation, doesn't matter. Qualitatively, one reproduces the same shape of slow growth and then AGN above. So that's my story about black hole. And now my last chapter, very recent, is about how the golden mass and the compaction events also drive disks and rings in high redshift. These are two papers, one just published, the other one submitted. First about disks. So again, back to the simulations. Same diagram of time and Virial mass. I could have used here the stellar mass. The color tell you how disky the average galaxy is in terms of rotation over dispersion. So in red, you find very non-rotational supported galaxies, irregular dispersion supported galaxies. And in blue, you find rotation-dominated galaxies, disks. And you find that there's a clear gradient as a function of mass at roughly the golden mass. You have irregular galaxy here, no many disks. Many disks dominate these massive galaxies above the threshold at all redshifts that are covered by this simulation, from 1 to about 8. What is the origin of this? Well, I can point you to one origin, and that's spin flips by mergers. So what's plotted here in the same diagram is the cosine of the angle between the direction of the spins in successive timescales. If you have a number here, blue, it means the spins don't change direction very much. It's a stable disk. That's what you have here. But if you have yellow or red, it means that over an orbital time, the spin of the galaxy flips to another direction. And this usually is caused by mergers of high sigma peaks in the nodes of the cosmic web. So these disks, which we saw here, are really where there are no flips that are perturbing these disks. But these irregular galaxies in the low mass regime are really suffering spin flips on a time scale that's shorter than the orbital time scale. So when a disk tries to form here, it's very quickly destroyed by another merger. Now, contrary to the belief that mergers are more efficient at high redshift, if you actually translate the dark matter halo merger rates to a baryonic galaxy merger rates, you find that they are not more frequent at high redshift. And the spin flips also destroy the galaxy here, but you allow disks even at redshift 5 and 6. This is the kind of disk I showed you in a movie earlier on, which was observed at redshift 4. Mergers don't destroy them here. So the moral is that disks can form above the golden mass at any redshift because they are not perturbed by spin flips. Now let me tell you about why I believe that the high redshift galaxies that looks like this are actually in most cases rings. So again, a picture from a simulation. This is the Virial radius. These galaxies are fed by cold streams that ride on filaments of dark matter from the cosmic web. They lose angular momentum as they move in. The angular momentum that is highlighted by the impact parameter with which they come in, and they spiral in because they lose angular momentum by friction. If I zoom in, you see that they eventually end up in the rotating ring at 10 or 20 or 30 kiloparsecs. The question is, what is the reason for longevity? We see many rings in the simulations. Why do these rings retain the angular momentum and don't lose it as they move in, as they have to supposed to shrink in? We saw this picture, how ring is forming. And the clue is that the compaction to a blue nugget and the central bulge has to do with this, with the longevity of the rings. These are several different galaxies in the ring phase post-compaction. The fact that we see many of them is consistent with the fact that they are long-lived. They live for more than a gigayear, sometimes several gigayears. Why are they long-lived? By the way, this is not a feature of only our simulation. I just collected pictures from the TNG50 simulation, very different simulations, with AGN. The worry was that maybe the AGN feedback will destroy those rings. As you can see, there are many examples of rings at high redshift in this simulation with very strong AGN. So the AGN does not destroy it. The AGN goes in the polar direction and does not destroy what happens into this direction. So why are they long-lived? This is a cartoon of this ring, and there are three players here. I want to compare three time scales. One is the accretion rate by streams. The other one is transport of mass, because this perturbed, unstable disk exerts torques on the ring, which pushes angular momentum out and causes transport inwards. What we require is that the accretion be more efficient than this inward transform for the ring to be long-lived. Otherwise, it will shrink before ring replenished. So that's one key condition. Then there is depletion, as we saw. The gas is depleted from the center by star formation and ejection by supernova feedback. And you need the depletion time to be shorter than the transport time, such that you'll see a depleted center and only star formation in the ring. So these are the two conditions for long-lived rings involving the three time steps. Now, these time steps we have computed a long time ago. This time step, we can time rate, we can compute by the star formation rate. This is hard to compute. And before our last work, I was thinking that this is going to be very efficient and rings will not be long-lived. But I was wrong. And let me show you in the last few minutes what the calculation actually did. We assumed that the transport inwards in orbital time units will be this factor delta D to the -2, namely it's going to be a short time when delta D is a Fourier unity. It's going to be on the order of one or few orbital times. Now this is the key parameter. It's the gas mass in the disk divided by the total mass, which is composed by gas, stars, and dark matter. In the new calculation, what we did is we computed the gravitational torques on such a ring by spiral structure, assuming a thin disk and tightly wound spirals. And we computed analytically what ended up as a longer time scale, especially when delta D is very small. When delta D is small, and this number allow you to get many, many orbital times for the transport inwards, which will allow the ring to survive. Now, how do you get a very small delta D? by increasing total mass. How do you increase total mass? By compaction events that go in and make the total mass by gas, stars, and dark matter much larger than it used to be before the compaction. This is what makes this number quite big and allow a long-lived ring. So just to summarize this, the time scale with the orbital time as a function of redshift, the accretion time as a function of redshift, the new calculated transport time, and the star formation time. And when you apply the conditions for efficient accretion versus transition, you get the delta T has to be smaller than this. When you apply the condition for empty center, you get this condition. So the bottom line is that once this parameter delta T goes under 0.3 or so, you're going to have long-lived rings. That's the condition for post-compaction. Just to show you some observations, an old paper by the Elmer-Greens was the first to see these very nice rings at redshift of other unity. Very clear rings around massive bulges. More recently, H-alpha star-forming regions, typical galaxy with kinematics. They have rings and bulges. These are 4 different examples. This is the profile of the gas density. And this is the H-alpha image showing these clumpy rings. We took all simulations. These are the 4 cases I showed you before. And again, we observed them with dust and resolution a la HST. And you see the ring, the blue rings around red bulges, massive bulges. This is 4 cases from Goods fields in Kendall's that we are publishing soon, led by Mauricio Valisco. And you see these very nice rings around massive red bulges. It's a great case where you make a prediction theoretically, and then you can see it observation. This is a more quantitative profiles, and you can see actually what you predict. We actually make prediction for ALMA. These are prediction simulation for ALMA of one of our nice rings. This is if you put the ring at redshift 1 and you like 2 hours of ALMA observation. If you put the ring at some lower redshift and you have only 2 hours of observing, you're going to see the ring in ALMA. This is the prediction for ALMA. I just want to end with reminding you that rings appear very near home. This is the famous ring in Andromeda, which has a massive bulge. This is a sombrero, always a nice gas ring, but it may be that the origin of redshift 0 is different. People argue that those rings occur at resonances in the disks, co-rotation resonance, outer Lippmann resonance. So they can be of a different origin because this story about cold streams bringing a lot of gas is really typical for the high redshift. So let me summarize my conclusions. There's a golden mass, which is responsible for this peak of star formation efficiency and peak of star formation efficiency as time. It's due to suppression of star formation rate at low masses and CGM heating plus 80 and above this. There's a wet compaction event, a dramatic event in the history of many galaxies that occurs at the same critical mass, the golden mass, and the blue nuggets responsible for many transitions in most galaxy properties, including metallicity, to Joe's question. Dekel growth is suppressed by supernova feedback in the low mass end, triggered by wet compaction at this mass when supernova feedback is inefficient anymore. And the resulting LGN helps maintaining the quenching. But here is not the trigger for quenching, it's just a maintenance mechanism. Finally, extended clumpy star-forming rings occur above the golden mass, supported by a massive post-compaction bulge that helps supporting the ring. And I stop right here. Thank you very much.
Thank you very much, Avishai. We're taking questions now. We cannot upload, but just virtually. So please feel free to ask questions.
Yes, Avishai. Sorry.
Yes.
Yes, Pablo from Universidad Autónoma de Madrid. I'd like to know what are the timescales typical for crossing the specific star formation rate plane?
Say it again, what is the?
Typical timescales for this quenching mechanism.
Okay. So the compaction event takes several hundred million years. So
Okay.
maybe 300 million years.
Okay, but no, we are not talking about gigayears.
No, well, once you quench, you remain quenched for many years.
Yeah,
You
sure.
can have another compaction event, but each compaction event happens on a dynamical timescale of the halo, a little less, and this can be maybe half a year, few hundred million years. Is typical
Right.
number.
All right. Thank you very much.
Yes, I have a question. This is Mark Baltzels. You talk very nicely about the formation of rings. I was wondering if, in your view, this is just one morphal formation of disks in general around the blue nuggets. So for the formation of the disks, massive galaxies today.
You were disrupted during your question, so can you repeat the question again?
Oh, sorry about this. I was wondering if the formation of rings that you have described has something to do with a more general question of the formation of disks, of the massive disks that we see around bulges today.
Yes, so I think that immediately after the compaction, you start forming a disk. And this is when the gas is still going inwards by transport and there's still a perturbation. And the first necessary condition for a disk or a ring is to be above the threshold mass such that merger-driven spin flips will be infrequent, less frequent than the orbital time. That's a necessary condition for a disk. Now, a second condition that you need in order to make the disk into a ring is these three conditions I was talking about.
Well, I was wondering more the opposite direction, going from ring to disk. Are these rings the precursor of the disks that we see today?
Normally what we see is that once you develop those rings, you don't really reform a disk in the middle. However, as you know, this accretion can be very hectic and things can come and go. Suddenly you can have a condition, you can have a merger, which will destroy the ring and make another compaction, everything will start again. So in principle, yes, you can have a ring and then a disk again, so on. But the usual evolution pattern is this, what I showed you here. this one. Well, this one. That you make a compaction event. Here, the disks are destroyed by mergers and counter-ring streams. A compaction end up with a new disk forming, and then the three conditions make you deplete the center. You have a inside-out quenching, and new streams bring in a new ring. Now, yes, eventually you can have this ring destroyed by some big merger or something, and you may end up restarting this process again.
I think, Karma, you had a question in the chat.
Yes, thank you. My name is Karma Gallard, and I study the very nearby universe, meaning the Milky Way and the local group. And I noticed that the Milky Way the Milky Way is very closely a golden mass galaxy that we can observe in great detail. And I wanted to ask you which aspect of the scenario you have discussed could be tested in the Milky Way, particularly with measurements of the Milky Way star formation history. Over time.
Very difficult question, because all these events really occur very nicely above redshift 1, redshift 2, and that's because you have these streams that bring in a lot of gas quickly, and this is the dominant feature that give you a ring and allow compaction event. Also, at redshift 0, all the mergers are not very wet. The galaxies are very stellar rich. When they merge, they can make an elliptical galaxy, or bulge, but they're not going to make a new disk. So the Milky Way was not massive enough at redshift 2 to really suffer from these events. It's becoming massive enough right now, but now everything is much more quiet in the neighborhood. So maybe when Andromeda merges with the Milky Way, we will have something more violent happening. But in the quiet history of the Milky Way, I don't think that much of these things really happen. And to testify, the Milky Way have a really relative small bulge. And so your question is very interesting, because we all care about the Milky Way, but I cannot add much. And in fact, the processes that probably govern the Milky Way and Andromeda today probably are more secular processes, where you have maybe rings, but they are confined to resonances in the disks. Secular evolution is more relevant. This behavior is very non-secular. It's very dynamical. Things change, the potential change over time scales, dynamical time scales. So I'm not sure I can really tell you much about recent evolution of the Milky Way, unfortunately.
So, but still, the golden mass that you were talking about was the mass at Z(2) or the mass today? I mean, the golden mass that you were mentioning of
the Milky Way is reaching the golden mass right now. So,
yes.
So, and indeed, I would predict that the Milky Way is in the process of starting to be quenched. Because the halo is now just becoming big enough for the CGM to be hot and to prevent supply of new gas. Maybe so it's going to probably quench, and Milky Way is probably going to enter the Green Valley very soon.
Okay, thank you very much. Thank you.
So we have a list of questions, I see. So Christina, go ahead.
Okay, thank you. Well, thank you very much for this inspiring talk, and I hope you can visit us when we are allowed to travel. Please come.
Okay, thank you.
And okay, so my question is about AGN feedback. So you said that it is, so AGN feedback would be just a maintenance mode, but it's not the trigger of the quenching, but it's the main quenching mechanism in the local universe, right? Below redshift 2, let's say, together with the...
I think it's a combination of gravitational heating of the halo,
yes,
and energy provided by AGN feedback that keeps it hot for a long time. You can really, the simulation I showed you, the Vela simulations, did not have an AGN feedback at all. And still, you had a nice quenching, or the beginning of quenching. Right. So these are simulations without AGN feedback. And you see that you have a trigger of quenching, and you can get quenched galaxies for a while. But you don't get them as deep as you want it to be quenched. And that's where AGN feedback comes in. Because the same process triggered the AGN. Now you can have the AGN helping you keeping the CGM hot. And this combination of hot CGM plus AGN feedback is the maintenance mode, I think.
Mm-hmm. Thank you.
I think John had a question. Yeah, go ahead.
Yes. Hello, Avishai. Nice to say hello to you. I have a question about ellipticals. And I see my friend Radekis has got a question, so my question might be the same as his question. But anyway, here I go. The stellar populations in the more massive ellipticals are older than the stellar populations in the less massive ellipticals. How does that fit into your scheme?
It's a good question. I think this is the general downsizing phenomenon, isn't it? The more massive ellipticals originate with progenitors that collapsed earlier and formed galaxies earlier. And then, of course, it's the massive disk. I didn't talk about mergers of massive disks, which probably form elliptical galaxies, massive ellipticals. So this was not part of my talk at all. I was talking about smaller scales. But I think the general idea is still valid, that the more massive ellipticals come from higher sigma peaks that started the formation and star formation earlier on. So despite the fact that in lambda CDM cosmology, the hierarchy is from small to large, you get this downsizing effect that tell you why the massive ones also have the older stellar population. I don't think I can shed more light on this right here. It's really on the massive end of what I was talking about.
Okay. Thanks.
I was focusing on the disk galaxies that are still star forming.
Yeah, sure. That's all right.
Alex, do you want to comment on that, or yeah?
Yes, in fact, I will have from another angle, let's say. Thanks, Avishai, for the great talk. It's really enlightening. I am Alexander Vasdekis. So in your talk, you didn't consider the possibility that the IMF or the IJIMF, okay, or galactic IMF, changes during the compaction process that you described in going from the blue nuggets to the red nuggets. So my question is, if you allow the IMF to change in that process, which means that it's going to be from a flat to a bottom heavy IMF, okay, in the process. so generating a larger stars, massive stars at the beginning, and later smaller stars. So the question is that then the supernova will change, and then the injection of energy, it will probably delay your the process, and make this let's say the overall game between, let's say, supernova feedback and the AGN, you know, and the golden mass you was describing to change. So any opinion on that? I mean, I have to say that from the stellar populations point of view, this makes sense, this scenario, and explains many of the observables through detailed spectroscopic analysis.
Okay, my simple answer is that I don't know. I have no idea. I didn't think about it. I do simple things first. I think it's a great, interesting idea. And the way I would address this is run simulations in which I incorporate a changing IMF or changing star formation recipe as a function of something. And you tell me what kind of recipe. I mean, the problem is, you know, our star formation recipes, as well as our feedback recipes, are very ad hoc. And in fact, different cosmological simulations implement different recipes and get different answers. So maybe adding another degree of freedom is a little pretentious, but maybe we should do it. So if you or somebody comes up with a nice, clear recipe that says, this is how star formation process is going to change because of a different density or a different something, then one can implement this in simulations or even in semi-analytic simulations, which may be easier, and then see if what you anticipate is going to happen really. It will be very interesting, but for this you really need a nice, concrete physical recipe. And it's not going to be easy. Oh, it's probably not going to be very robust. It's going to be ad hoc. That's the problem.
Well, just to, I mean, this is several ongoing new frameworks for that, including the IGIMF, which is the Integrated Galactic IMF, that during the high star formation rates implies the more massive stars. Okay, so you can, this is one possible scenario. We found relation with metallicity, for example, that the lower the metallicity, the less, the flatter and more steepy for higher metallicity. So there are several, I agree with you that there is no framework right now, a robust one, to describe from the theoretical point of view this extent, but it is, there are several scenarios right now being investigated. Thank you.
So I think yeah, go ahead, Avishai, if you want to comment.
It's a nice challenge.
So it's been already more than an hour now. We have at least 2 more questions on the queue. I don't know, we can take these 2 last and then we break, because otherwise it's a bit too much. So Mark, you wanted to say another thing, or?
Yeah, I wanted to, about the nuggets, the red ones actually. There have been measurements of velocity dispersions, and for a while this was that was the way to get the masses of these objects, dynamical masses. And we got stuck with the question that the dynamical masses turn out to be below the stellar masses determined from stellar populations. it's a question that was never really fully resolved, I believe. And I was wondering if you had thought or had looked into that, comparing simulations or data or whatever.
Well, in fact, yes. In the simulation, we look for the different components, the stellar mass, the dark matter mass, etc. And in fact, I'm involved in writing a paper now, trying to give prescriptions for how to estimate the dynamical mass from observations, kinematic observations. And it's not always the simple recipe that people use with the Virial relation and so on, that leads people to sometimes get stellar masses which are larger than the dynamical masses. So we're writing a paper just about this recently, so this will be useful. When you have the compaction, you bring in gas, you make a stellar bulge, but you also make the dark matter contract inwards by the contraction. So everything becomes more compact. This is exactly why you get a bigger mass in the middle that can be even dark matter dominated. And this central mass is what allows you to get these rings. And it doesn't matter what it's made of. And in fact, if you look at the paper we submitted, there is some graphs, some plots that show you whether the blue nugget or the red nugget is dark matter dominated or baryon dominated, and by how much. And to my surprise, sometimes it's baryon dominated, it's dark matter dominated. In the inner 1 kpc, it's always baryon dominated. But inside the ring of 10 kpc, the dark matter can be very important. And that's because the dark matter was attracted inwards by the baryonic contraction. So I think your question is very good, and it's partly answered in this paper. You can have a look.
Thank you.
So we'll take a last question by Mike.
Hi, Avishai, I'm Mike Beasley. So my question is related to Mark's comment. So there are some observations of nearby, what we think are red nugget counterparts, and they tend to, so these are very compact, massive galaxies, and they tend to appear baryon dominated in the centers, or at least even out to 3 effective radii. And so you mentioned in your talk that during this compaction process, there's a switch from being dark matter dominated to baryon dominated. So could you just explain a bit more what the process is to make this switch? It's not an absence of dark matter, it's just in the concentration of baryons in the center, is it?
Exactly. It's exactly the fact that gas is losing angular momentum and can shrink. The dark matter cannot shrink by itself, and the stars cannot shrink by themselves because they're non-dissipative. So only the gas can shrink once it loses angular momentum. And whatever causes this, a merger or counter-rotating streams, it is brought to the middle and increasing the baryon density while the dark matter remains roughly the same. That's all. Now, at low redshift, it's a good question. It's going to be very rare. You may find some counterparts, but not very many. Where I predicted redshift 3, almost every galaxy goes through such a phase. At redshift 0, it's going to be very outliers. Maybe because there was a wet merger happening or some other trigger that brought the gas in. So these outliers are very interesting to look at. And I'm not sure that everything I could say about what I learned at redshift 2 or 3 is going to valid at redshift 0. It's a different environment. The cosmic streams are not as dominant. You have to be more careful. But still, we have mergers even today. So yes, maybe it's a merger-triggered compaction event. Why not?
Okay, thanks.
Okay, so I'll take the chance to ask a very quick question. I don't know if Avishai, I think you at the beginning you mentioned something about the recent paper of ALMA of big disk at redshift 4. I think you're referring to this Prochaska paper in Nature. I don't know if it was that.
Yes.
So you mentioned something that you see something similar in the simulations. Can you briefly comment on that? Or
Well, I'm saying that they claim that it's very revolutionary to see disk at redshift 4, the logic being that the merger rate for halos at redshift 4 is higher than it is today. And the naive assumption would be that even if you are in a halo of 10 to the 12 solar masses, you will not retain a stable disk because the mergers are so frequent that they're going to destroy the disk, even in a massive galaxy. Well, the main point we made in our recent paper about this is that the merger rate for halos is not the same as the merger rate for galaxies, because there is a stellar to halo mass ratio which varies with mass. And if you take this variation into account, you find that the merger rate at a given mass, the merger rate for baryonic masses is not going up at high redshift. So if you are massive enough, it remains low and the disks can survive.
I see.
And this is why we predicted you can have nice massive disks at redshift 4 or 5 or 6.
I see. Thank you. Okay, so I think it's time to break. Thank you again, Avishai, for the very nice talk.
Thank you very much for listening and for having me and for the great questions. I think people were actually listening, so it was nice.
And yeah, so we clap virtually, and I hope you will be able to visit at some point.
I'm sure I will.
So yeah, thank you very much. And I will send you the link with the video, which is recorded in YouTube. Thank you very much, everybody. And
bye-bye, everybody.
Bye.
Thank you.